Okay, so in this lecture, we are first going to continue our discussion on the using momentary function to find the distribution for some other function of random variables. And then after that, we will focusing on the normal distribution. And then we will be mainly deriving the mean and the variance for the normal distribution. Okay, so so for our discussion on the momentary function, so so suppose we have a new random variable x that follow a Poisson distribution with parameter lambda, and here we are going to use a subscript 1 to make a distinguish between the random variable x and also the random variable y, which also follow a Poisson distribution but with the parameter lambda 2. So now we have two random variables and then also two parameters to consider here. And then we also know that x and y are independent. So now the question is, what is the distribution of x plus y for this new random variable that we define as the sum of x and y? And then we're going to use momentary function to find the distribution for x plus y. Okay, so now let's set up the momentary function for this new random variable of interest. So here I put the x plus y in the subscript to refer the random variable that we are interested in. And then because we know that they are independent, we can rewrite the momentary function for this sum as the product of the momentary function for each of them. So here I'm going to write the momentary function for x and then the momentary function for y and then their product. And this is because they are independent. And this is also related to the properties of the momentary function that we introduced last lecture. Okay, so now that we have decomposed into a product, now we can just plug in the momentary function for the Poisson distribution. And this is also something that we derived earlier. So for the momentary function for a Poisson distribution is e raised to the power of lambda and then et minus 1. However, one thing to point out here is that the random variable x follow a Poisson distribution with parameter lambda 1. So here we also need to make sure that we put a 1 here to distinguish between x and y. So now we also write the momentary function with a lambda 2. And this is the momentary function for y. And now we just need to simplify this, and then we can check what is the distribution for this x plus y. So here we can write e of lambda 1 plus lambda 2 multiplied by et minus 1. And this is because of this property that we have been used very often. So exponential of a plus b. Okay. So now let's look at this expression. And you can see their resemblance to the momentary function for a Poisson random variable, except that the lambda looks very different. So now we can conclude that the x plus y also follow a Poisson distribution. And this is because you can see that the resulting momentary function is very similar to the momentary function of a Poisson distribution. The only difference is that the parameter is updated. So the parameter for this new random variable x plus y will be the parameter here, so which is lambda 1 plus lambda 2. And we can conclude that the new random variable x plus y also follow a Poisson distribution, but has a parameter that is lambda 1 plus lambda 2. Okay, so that is our first example. And now let's consider another example. So now we are going to have not only 2 but n copies of random variables, and then all of them are independent, identically distributed from a Poisson distribution. So note that here we are not going to use a subscript to distinguish them anymore, because they are all identically distributed with the same Poisson distribution or with the same parameter here. Okay, so the question for this example is to use the homogeneity function to find the distribution, or maybe let me write it down. Use homogeneity function to find the distribution of t, which is the sum for all n random variables. Okay, so again, as our template, we write down the homogeneity function with respect to the parameter of interest here, which is the capital T. And then because they are independent, which is just the homogeneity function for x1 multiplied by the homogeneity function for x2, and then multiply all the way to the homogeneity function for xn. And now we can write down the homogeneity function for Poisson distribution again, which is the exponential lambda et minus 1. And this is for one copy of the random variable that follow or has a parameter of lambda. But because we know that they are identically distributed, so here let me put identical. And then that means each of the random variable xi, they all has this form for their homogeneity function. And essentially, we have n copy of them, which is just this formulation raised to the power of n. And this will give our result as n lambda multiplied by et minus 1. And this is like using this property here. So EA multiplied by EA multiply all the way to EA. And this is equal to E of A and then raised to the power of n times. Or you can use A plus A plus A, and then you have n copy of them. And this is equal to E of A and then multiply by n. You have n copy of them. Okay. Now let's revisit our question here. What is the distribution for this random variable t? And now by looking at this formulation, we recognize that this is also in the form of the homogeneity function for a Poisson random variable. So that this random variable t also follow a Poisson distribution. And then the parameter is n multiplied by lambda. Okay, and that's for the Poisson examples. And let's do one more example, which is for random variable x that follow a binomial distribution. And then here we are going to make the distinguish between two random variables by their number of tosses. So binomial distribution is also a distribution with two parameters. So here we have the x followed binomial but with n1 tosses, and then probability of landing on head equal to p. And then for y, we also have a binomial distribution, but the parameter is n2, and then it shares the same parameter p. And also we know that x, y are independent. So the question is, what is the distribution of x plus y? Okay, so again, just as our template, let's write down the moment-generating function of parameter of interest. And then because they are independent, this is the moment-generating function for x multiplied by the moment-generating function for y. And then now we just need to write down the moment-generating function for a binomial random variable. So this is also what we derived earlier, which is the probability p multiplied by et plus 1 minus p. And then raised to the power for their number of tosses. So for x, this is n1. And then for y, because they share the same p, so that we have this, and then raised to the power of n2 for the moment-generating function for y. Okay, so now we just need to simplify this, and then it will result into p. So for the basis, it stay the same. And then for the power, it's just n1 plus n2. So now, by looking at this formulation, we also see their similarity from a binomial moment-generating function. And then we can claim that x plus y also follow a binomial distribution, except that now the number of tosses is n1 plus n2. And then the probability is still going to be p for landing on head for n1 plus n2 tosses. So this is only true when the probability is stay the same between the random variable. But if you have a subscript for the p, then this is no longer true, and then you will have something else for your moment-generating function. Yeah, but this should conclude our example for this bivariate binomial. So two random variables, and each of them follow binomial distribution. Okay, and before we talk about the normal distribution, now I would like to talk about a little bit regarding some other properties for the moment-generating function, besides the formula that we presented last time. So the first one, so these are for the moment-generating function. So the first one is that let's denote, so let me introduce some notation first. So let's denote the phi of t as the log transformation for the moment-generating function for random variable x, and then which is a function of t. Okay, so just a log transformation. And then I'm going to make the following, or I'm going to specify, to talk about the following result. So the first one is that the first order derivative for this log of moment-generating function, and then you evaluate t equals 0. This is equal to the expected value, as we are using, so similar to the result when we use the moment function and then first order derivative, like that. What is different is for the second result. So when you take the second order derivative and then set t equal to 0, you would directly get the variance for x. And for the moment-generating function, when you take the second order derivative set equal to 0, this is equal to the second moment, but not the variance. You need to minus the square of the first moment, and that will give you the variance of x. Yeah. But when you take the log transformation, you will directly get the variance of x. Okay, so now I'm going to to prove or to show that these equations are true. So let's say for the first one. So let's see, this is the phi of t, and then taking the first order derivative, which is just the dt for the log of the momentary function for that. And then using the chain rule, let me just to make a distinguish. Okay, so for that, the chain rule, you will have a one copy of the momentary function in the denominator, and then for the chain rule, you will have the derivative for the momentary function on the numerator. So there's no derivative on the denominator, but there's a first order derivative on the numerator. And now we're going to evaluate this equation at t equal to 0. So for the momentary function, without taking any derivative, and then when you evaluate t equal to 0, they should always be 1. You can verify this by our intuition, or when we first introduced the momentary function, we use the infinite sum to introduce the idea of momentary function. You can revisit that formulation and then evaluate at t equal to 0 to check whether this is true or not. But what I'm claiming here is that when you evaluate t equal to 0 for the momentary function, you always equal to 1. And then for the numerator, this is equal to the expected value when you evaluate t equal to 0. This is by our also by our or what we showed earlier for the first order derivative. So that will give you the result, which is equal to the first moment here. Yeah. So next we are just going to show the second result, which is a second order derivative for the log of the momentary function. So now also dt, but now we're using this expression because this is the first order derivative. And then we're taking another or second order derivative. And now we are going to use the quotient rule. So for the quotient rule, the orders is going to matters in this case. So for the denominator, you just have the square for the denominator. But for the numerator, the orders matter here. So you first take the derivative for the numerator, multiply by the denominator, and then you have a minus sign. So this sign here also matters. And then you will have this from the numerator, and then also another derivative on the denominator. So also a first order derivative for the denominator. So now when you evaluate at this t equal to 0, for the denominator, you have a 1 and then raised to the power of 2, which is also a 1. But for the numerator, you have a second order derivative for the momentary function, which is already the second moment. And then for this one here, again, this is just a momentary function, and evaluate t equal to 0, you will get a 1. And then you minus this is a first order derivative. So this is just the first moment. And then you have two of them. So that's the square. And then you have the variance of x. Okay, so then you immediately get a variance for the log of the momentary function. Okay, so that is two other results that I want to demonstrate here. And now we can talk about the new topics on the normal distribution. Okay, so our new topic today is the normal distribution. So we are going to write the normal distribution as the random variable x that follow a normal, and then with mean mu, and then the sigma square for the variance. And then the support for x, it's in negative infinity to positive infinity. And then for mu, it's just a real value scalar. And then for the sigma square, it has to be a positive real value. So that is the support and then the constraint on the parameter. And now I'm going to provide the probability density function for the normal distribution. So I'm going to write f of x. This is 1 over square root of 2 pi and then sigma square. And then exp for 1/2, and then x minus mu, and then sigma. And then this together, taking the square, closing the parenthesis. So this is for a random variable x that follow a general normal distribution. And there's also a special case, which is called the standard normal. And then people usually write a z for standard normal random variable. And this is for a normal distribution from 0 and 1. So this is the new mean, and then this is the variance. So translate to the density function. You will have 1 over square root of 2 pi. And then the sigma square is just a 1 here. And then you will have a exponential negative 1/2, and then z square. Because this is 0, this is 1, and you have a square. So that is the formulation for a standard normal random variable, or a probability density function. And here I would also like to introduce the transformation between a general normal distribution and a standard normal distribution. So now let's say for x that follow a normal distribution with mean mu and sigma square. And if you write x, or if you transform this random variable x minus the mu over the standard deviation, and this new random variable here will follow a standard normal distribution. So this is one transformation, convert from general normal to a standard normal. And now suppose you have a standard normal distribution. And now if you denote x, that is equal to sigma multiplied by z plus mu, and this will follow a normal distribution with mean mu and then sigma square. So this is that we want to convert a standard normal random variable to a general normal random variable, but you need to provide the sigma and then the mu. Okay, now we are going to talk about the normal distribution as well how we introduced the distribution before. So we are going to focusing on the e of x and then e of x squared. and then also the variance of x, but which is just a formula between of these two quantity. Okay, so now let's begin for e of x. So now we're going to use the definition, taking the integral from negative infinity to positive infinity, and then x multiplied by the probability density function. Then dx. So now we are going to make the change of variables, because as you can see that there are two places that have x. So that means we need to use some technique to handle this case. So for example, we have used integration by part to handle for the, I think, the exponential distribution. And here we also have that case, so we need to consider that. So let's see what else we can do here. So let's set y equal to x minus mu over that, which is this one here. So that x is just equal to sigma multiplied by y and plus mu. And then dx is just sigma dy. Okay, so now let's make the change, or to replace the component here. So we will have sigma multiplied by y plus mu for the x. 1 over 2 pi sigma square that exp 1/2 y square. And here, don't forget, you have a copy of sigma dy. So now everything is about y. And also for the lower bound, upper bound, plug in negative infinity and positive infinity here, you will have that as well. So now we just need to further simplify that. So now I'm going to break the sum here into two parts. And also I'm going to cancel this sigma square in the denominator with this sigma here, because this is under the square root. And then I'm going to just cancel those, and then they will disappear. So what we get is a integral for a sigma multiplied by y from here, 1 over 2 pi. Okay, so maybe let me write in this way. So you have a sigma from here over square root of 2 pi from here. And then you have a copy of y, and then a exp 1/2 y squared dy. So that's for the first part. And then you also have a integral for mu over 2 pi from here, exp 1/2 y squared dy. Okay, so now I'm going to use another result that to simplify this two integrals here. So first of all, we're going to say that this y here, this is a odd function. Which have the following properties, which is f of negative x. So we say a function is an odd function if f of negative x is equal to negative f of x. So you can check for this y. If you input a negative value, you essentially get a negative of the original function y. So that's that. And now for this part that I underline, for this exponential terms, this is an even function. And the even function has the following definition. F of negative x is equal to f of x. You can also plug in any values to verify, as there's a square here. Okay, so now you have a product of an odd function and even function. And this will also give you an odd function. And what we have that is different from before is that we evaluate the integral at this from negative infinity to positive infinity. So in this case, now the integral for an odd function is equal to 0. And this is the case only when we evaluate from negative infinity to positive infinity for an odd function. And then we know that this is going to be 0. So next, we are just going to analyze the second term here. So a constant, and then we move it outside. And then this is the part that involving the random variable y. Okay, now I'm going to mention another property for the normal distribution, which is this one. So the integral for negative infinity to positive infinity, and then exp y squared dy. This is equal to a constant, which is 2 pi, which is also part of the normalizing constant in the normal distribution. So now that this entire integral will reduce to square root of 2 pi, and then the whole thing is just equal to mu, because square root of 2 pi will cancel out with that, and then you are only left with mu, a single copy of mu. And we started by e of x. So the expected value for a normal random variable is going to be the mean mu here. Yeah. So this result you already know, but what I'm showing is the derivation to get this first moment here. Okay, next I'm going to show e of x squared, which is the second moment. Okay, so again, from the definition, I'm not going to write the upper bound, lower bound. I will only add them when we talk about them later on. So we have that. Okay, so now we are also going to use the trick that we write, let's say we set y equal to x minus mu and sigma. So that x is equal to sigma y plus mu. And then because we have an x squared here, we also need the x squared. So sigma square y squared plus 2 mu sigma y, and then plus mu square. Okay, and then we have the dx equal to sigma dy. And now we are going to bring all these components into the integral here. So let's write it here. Sigma square y square plus 2 mu sigma y plus mu square 1 over 2 pi. So I'm going to cancel out this sigma square with the sigma from the dx. One half y square and then dy. Okay, so now again we're going to break this integral into 3 components. Okay, so starting from here. And let's see, y square over square root of 2 pi from here, and then integral y square exp 1 half y square dy. Okay, so that's the first part. Okay, now let's work on the second part. Let's see if there's any way. So 2 mu sigma over square root of 2 pi, and we have y multiply by that. Okay, so now by looking at this, even this is an odd function, even function, so this will go to 0 right away. And this is only because it's evaluated at that upper bound, lower bound. Okay, and now for the last part, let's see if you have space. Maybe let me put it here. Okay, so y mu square over square root of 2 pi integral exp negative 1 half y square dy. Okay, so now this thing just square root of 2 pi, and that will give us, so this part, let me copy it down first. And this is because of the odd and even function. This is plus 0. And this is equal to square root of 2 pi. And this will give you mu square. Okay, so now the question is, how do we evaluate this one? So now I'm going to provide another tool for you to further simplify the first term here. So let's set alpha equal to 1 half. Okay, so I'm going to write in the following way. Negative alpha y square dy plus mu square. Okay, so now we want to work on this term, the part that I underlined, and I'm going to write it in the following way. Integral, and also that's that. But I'm going to write this part, let's write in the square bracket. So d alpha a negative sign here negative alpha y, and closing the square bracket, and then dy. Okay, so now, okay, there's missing a square. So if you take the derivative for alpha, you will have a copy of negative y squared in front. The negative sign cancels out with that, and then you will have the y squared here. And then this inside the square bracket will give you the part that I underlined here. So this is essentially, so this is still the same. But when we write it at the differentiation here, we can make the change for changing the order of the operation in the following way, which is sigma square over 2 pi, and then d alpha, but integral from that. Then let me also put the negative sign here. Dy plus mu squared. Okay, then let's see. So okay, so now we need to do one more change of variable, which is to let z, let's introduce another letter, to be 2 alpha multiplied by y. Then this y is equal to z over 2 alpha, and then dy is just 1 over square root of 2 alpha multiplied by dz. Okay, so now let's change the component here. So let's see, y squared. So you will have z squared over 2 alpha. Okay, and then dy is just 1 over 2 alpha dz. Okay, so let's further simplify from here. And then d alpha. So now this alpha and this alpha cancel out. You will have okay, so let me see. Okay, good. I'm going to bring this constant also outside. And okay, so yeah, when you do this kind of things, make sure you don't mess up with the order. So d alpha, let's use the square bracket here. So the constant only moving outside the integral, but you cannot move further before the differentiation. And then closing the square bracket. Okay, And then let's further simplify. So you will have something like d alpha. And then for here, you will get this is equal to square root of 2 pi. So in the square bracket, you will have pi over alpha, and then square root of that. Now let's evaluate this differentiation. So you essentially have square root of pi multiplied by alpha negative 1/2. Okay. And then you have a negative 1/2, but alpha raised to the power of negative 3/2. Okay, so no more differentiation or integration anymore. And recall that alpha that we define as 1/2. So now we have a copy of 1/2, and then also 1/2 raised to the power of that. So this is essentially negative sigma square over square root of 2 pi. Okay, later we'll work on the pi here. Also, the negative sign cancel out here. You will have 1/2, but raised to the power of negative 1/2. Because this is a 1/2 raised to the power of 2/2, and you minus 3/2, so you only have one copy of 1/2. And also don't forget there's a mu square somewhere from here. So there's all a mu square afterward. So that's that. And then you will see that this is essentially just square root of pi and square root of 2. Square root of 2 pi. You have sigma square plus mu. And then you essentially or eventually have mu square plus sigma square. And then again, this is the second moment that we started by the definition here. This is the definition. And then we use different mathematical tools to derive this statistical quantity here. Okay, so now just revisit our quantity so far. E of x equal to mu. E of x square sigma square plus mu square. So that variance of x equal to the second moment minus the square of the first moment, which is sigma square plus mu square minus mu and then raised to the power of 2, and that will give you sigma square. And this is the variance for a normal random variable. So what we did here is just starting from scratch to prove or to show that the second moment is equal to this, and then you get the variance for a normal distribution sigma and the expected value equal to mu that I'm pretty sure you already know for a very long time, but we are just going to show this result, and also by So introducing this statistical concept along with some mathematical tools for you to derive this kind of quantities. Okay, so I will stop here.